Boom! Yes folks, Hume here again. So in this video we're continuing in our series on Pythagoras Theorem. In the last video we would have worked out a simple case of integers that conform to Pythagoras Theorem, 3, 4, 5. In this case we're going to do the same thing, but we're going to use numbers that are not integers. So in other words, we're just giving you a little idea of what could happen, what would normally happen in a Pythagoras Theorem question, in a Pythagoras Theorem situation. Most times, let me say 8, 7, 8, 9 times out of 10, you will get a situation in Pythagoras Theorem. All the numbers wouldn't be integers. You might get one integer or maybe two integers. You will hardly ever get all three being integers. Excuse. So what I would have done here, what I'm going to do here now is work out one where none of the lengths are integers, just to give you a feel for what would take place, the kind of situation, the kind of what it would look like when you're actually doing the calculation. So we have a situation where we have a right angle triangle here. The length of one side is 10.5 and the length of the other side is 5.2. So in this case, the length we're looking for is the hypotenuse h. So we start off by labeling the hypotenuse. Alright, and of course we know the formula. The formula is that h squared is equal to, in this case it would be 10.5 squared plus 5.2 squared. And yes, in a case like this, we definitely need the calculator. Alright, so 10.5 squared is equal to 110.25, 1110.25 plus 5.2 squared is, let's see, 5.2 squared is equal to 27.04 plus 27.04. So now we just perform the arithmetic as before. So you're adding that now, 110.25 plus 27.04. 137.29. So the square of the hypotenuse will be 137.29, which means then that the hypotenuse would be the square root of 137.29, and that is equal to to the power of 11.7, let me say 11.7. That is equal to 11.7. Good. So this is the exact procedure that we would have used in the last video with 3, 4, 5. The only difference is that we have numbers that are not integers now. So just as we did in the last video, we're going to do the same thing now. We switch up, we flip the script a little bit. So let us say, for the sake of argument, that we had 11.7 there, and the one that we didn't have is 10.5. Alright, so in this case now I'm going to use, just for the sake of maintaining the consciousness of trigonometry as the flip side to Pythagoras Theorem, as something that is allied to Pythagoras Theorem. Let us, for the sake of argument, use this guy up here as a reference angle. Good? So we don't have to concern ourselves at this point with what the angle is, how much degrees. We don't need to know that right now. All we need to know is that we don't have this side. In this case now, this side here will be the opposite side. Right, so I'm making sure to keep hammering home the point, right, so that it will stick. So in this case, we start with the 11.7. So 11.7 squared, we have that as the hypotenuse, is equal to the opposite squared plus the adjacent side squared. The 5.2, of course, being the adjacent side because it is next to the reference angle. So 11.7 squared would be what? Let's see. 11.7 squared is equal to 136.89. Alright, so 136.89 is equal to opposite squared plus 5.2 squared is what? 27.04. That's what it was. 5.2 squared equal, yes, 27.04 plus 27.04. Right? Same thing. Now in this case, because we already have the hypotenuse, we have to take this and carry it across on that side. So your next step in the arithmetic would be to say that 136.89 minus 27.04 is equal to the opposite squared. We check that out. Let me see. 136 minus 27 would be 109.85 is equal to opposite squared. Boom. Bam. Right. Yeah. If I see something that where I don't need to use the calculator, we just work it out and proceed. So O now, which is the length of the opposite side, will just be the square root of this. So the square root of 109.85 is equal to O, which is equal to square root of 109.85 is equal to, let us guess, 10.48, which is equal to 10.5. Right? You get the same 10.5. And of course, we're going to flip the script again, and instead of the opposite side, we're now trying to find the adjacent side. So if we had this and this, 10.5, and we didn't know what this side was, right? That is the adjacent side. Right? So we go through the same procedure that we just went through. So we start off again with the original Pythagoras Theorem formula. So in this case, it will be 11.7 h squared is equal to opposite squared, 10.5 squared plus adjacent squared. Right? So the 11.7 squared would be 11.7 squared is equal to 136.89 is equal to 10.5 squared is equal to 110.25 plus a squared. A, of course, being the adjacent. And of course, just as we did in the last working, we take this and we carry it across here. So you have now 136.89 minus 110.25 is equal to a squared. So let us see, minus, we could do this mentally too, right? 89 minus 25 is 64. 136 minus 110 is 26. So you get 26.64. All right, hold on. Let me see. 136.89 minus 110.25 is equal to, yeah, 26.64. Right. The reason why I seem to be doubting myself there is because in the two previous workings we had 5.2, which 5.2 squared is 27.04. But these are the kind of slight discrepancies you will get when you're dealing with decimals, right? They wouldn't line up exactly all the time because of little errors that you will get based on the number of decimal places that you use. Good, but we will discuss that in a separate video at some point. But generally, you will have some idea of how accurate you want to be with the answer, whether it's 1 decimal place or 2 decimal places, or 2 significant figures or 3 significant figures, that kind of thing. All right, and of course, it means then that you must be able to express any number to any particular number of decimal places or significant figures. That, of course, we would have covered in a separate video. So back to our situation here now. So the square root of 26.64 is equal to a, which is the adjacent side, excuse, and that is equal to 5.16, which is 5.2 to one decimal place. I was kind of concerned, I was kind of worried that it would have ended up being 5.14 or 5.13 or something, in which case I would have had to use 5.1, but it worked out pretty well. Good. So even though there were some discrepancies with the squares and the square roots, when you work everything back to one decimal place, you get the original figures that we would have had before: 11.7, 10.5, and 5.2. And what I want you all to understand is that at the basic, most fundamental core, this is what Pythagoras Theorem is about. Pythagoras Theorem in 2 planes, of course, but you have Pythagoras Theorem in 3 planes too. Well, 3D Pythagoras, which is basically you have a 3-dimensional shape, and within that 3-dimensional shape, you have a kind of plane shape inside there. We will deal with that inside the COVID part. Right? I'm not even going to try to make a video on that, because that is one of those things where you have to actually see the problem and bounce your head and figure it out. Alright? But I just throw that out there as a teaser to show you that the problem wouldn't always be about a triangle on a plane surface, on a piece of paper or a whiteboard or a floor. Right? You might have to find the length between some point in a room to some vertex on the top of the corner there. But forget that. Back to what we're doing here. Right? Any problem in Pythagoras Theorem is basically some variation of this. You have 2 sides and you need to find the other side. That is the basic, that's the most basic application of Pythagoras Theorem. Of course, now, for the purposes of exam and in real life situations, you would almost always have some level of interest in the measurement of the angles of the right angle triangle. So you might need to find out the height of a wall, or the length of a ladder, or the distance from the foot of a cliff to a boat in the sea, or something like that. Right? In that case, usually you would have to incorporate some consideration of the angles involved, whether it is this angle here or this angle here. So you might have a situation where you're standing up at a point and you're looking up. This, in a situation like that, would be what we refer to as the angle of elevation. That would be a reference angle. Or you might be on top and you're looking down. Right? In this case, the angle of depression would be this angle here, which would then give you this angle here by default when you minus it from 90. But again, don't worry too much about that. Yes, what I like to do when I'm talking is to show that whatever we're doing at a particular point in time has applications in other things. So sometimes while I'm talking about one topic, I might veer off for a little while into other topics and then come back. That is not necessarily an invitation now to go study in some other topic. Right? We're doing what we're doing here, and when we master that, then you have the platform to go on to do other things that would necessitate, that would need the knowledge that we're dealing with now. Good? So that is basically it. That is basically it. All there is to Pythagoras Theorem. So any further videos from me on this topic, after the next video, of course, would be basically doing a couple live past paper exam questions, right? Exam type questions, whether it's CXC, CSEC, or Cambridge, or whoever, right? Problems abound all over. Good. So I want to encourage you who looking at this, if Pythagoras Theorem is one of the things that giving you trouble, I hope that you would have been gaining some level of understanding, some level of comprehension, all right, by looking at the videos. But I want you to understand that the real understanding is formed when you do the questions on your own, because there are so many different ways they could throw the questions at you, right? There's only so much different permutations we could cover in a 10-minute video or a 15-minute video. Right? All we're doing here is just giving the foundations so that now we're in a position to open your textbook or go in my online setup, check out the questions. Alright? And in that now, you go a further step now in your learning process. And then the next step now would be to be able to do that under pressure. Under the pressure of an exam situation where you have a time constraint now. So in other words, you don't have the whole weekend to do a question. You have a set amount of time. How much ever minutes? 10 minutes, 15 minutes, 12 minutes, 18 minutes, 14 minutes. And you had to solve the question from first thought to the last stroke of the pen in that particular time frame. And you do that for a number of questions over the exam. So all of this is more than just about learning maths. It's about developing certain types of behaviors so that we understand that no matter what you do in life, at some point you will be called upon to perform under pressure. Right? It might be pressure of time, it might be pressure of a crowd watching you, it might be the pressure of a boss, or the pressure of some expectation of somebody, or something. So we don't want to get this idea, people have this idea that people shouldn't be doing exams. No. There are a whole set of arguments about whether exams are necessary or not. But for me personally, especially with the younger ones, the 14 and the 15 and the 16 and the 17-year-olds coming up, 18, 19 or whatever, the earlier you understand that pressure is part of life, the better. So you don't go through your whole life expecting that everything will be easy and nice all the time. So doing an exam is a nice way to get into that zone. Yes, you see the topic, yes, you understand it, but understand that there's a higher level now of you had to do this under pressure, and that is part of your preparation. Understanding that you now will be called upon to perform under pressure, that is part of the thing, that is part of life. Alright? So, yeah, get a little philosophy every now and then in the mix up too now. Good? So that's it for now. We have something coming up in the next video where we will deal with what we refer to as Pythagorean triplets, where we have a certain number of trios, integer trios, that conform the Pythagoras theorem. So look out for that coming up next.